All right, last try. Hello, my name is Grant Weesey, and this is my project for CMSE 201, Probabilistic Fortnite Simulations. So a little motivation of why I wanted to do Fortnite. I wanted to demonstrate the simulation in Python using probability. I also wanted to look at skill growth over time and how that affects the possibility of winning. And also, as a little side note, there's not going to be any code in this presentation. It's going to be very theoretical level, so we can quickly get into some of the statistical analysis and the graphs. So looking at our research objectives, first, is simulating Fortnite games possible, even with a probability simulation? What are its limitations when you're doing that versus like a agent-based model? How do player statistics change game outcomes? And how does skill change player outcomes? Can skill change over time? So, is simulating a Fortnite game possible? What are its limitations? Before I wanted to get to that, I wanted to talk about what Fortnite was. So Fortnite is an online video game where 100 players spawn on an island. As players find gear and explore, they eliminate each other and try to be the last player left standing. Fortnite has multiple modes where you can have teammates and such. However, this project focuses on solo games, where it's you versus 99 other people. But when we look at this picture, these guys have a lot of different weapons here. This person is collecting resources. This person has built something. And there's a lot of different terrain that in the Fortnite island. So unfortunately, because of the nature of my project and the scope of what we're doing in this class, I can only really focus on the individual player parameters, like their skill level and how much experience they have. So how would a simulation even work? It's basically throwing a lot of dice at a lot of times, but it actually can get really representative of real life. So a high-level view of my simulation is this flowchart describes one simulation. So first, we set the player skill and experience. We generate 99 other players with pseudo-random skill levels, and then we take 100 players and randomly put them into 50 groups of 2. Then, based off of each player's skill levels, we eliminate 1 player from each pair. Then we take 50 players and put them into 25 groups of 2. And then we do the same thing until there's only 1 player left. Then we return the winner of the simulation. We repeat this many, many, many times and derive a certain statistics that can be useful in helping analyze what the simulation is doing. A few questions that I want to answer here is, what exactly does player skill mean? Can you define that? How do you generate 99 other random players with pseudo-random skill levels? And how do you even eliminate players? So first of all, when you set player skill and experience, what does that mean? In my simulation, there are 3 parameters that go into generating skill: accuracy, previous rounds played, and first-person shooter experience. I know Fortnite really isn't first-person, but it's general shooter experience. So accuracy is defined by the percentage of shots that hit their target. Previous rounds played is defined by the total games of Fortnite that have been played by the player, and FPS is defined by the amount of previous FPS games the player has played before. Alpha, sigma, and delta are important to the write-up in my project when putting these into equations. So my accuracy, well, before I get into those confusing graphs, I wanted to ask, how do you generate 99 other players with pseudo-random skill levels? How does that work? So basically what we do for each variable that we consider, I have a random number generator that creates a distribution of possible values and generated for each generated player. So you're generating the first player, you would take a random number from this distribution, a random number from this distribution, and a random number from this distribution. That would be player 1. You would do this with the 98 other players. This distribution right here works in this following way. It's skewed in a way that it makes the probability of choosing one number over another much higher. For instance, the accuracy distribution with an in the accuracy distribution, the average accuracy is 15%. So there's over 600 values that fall in the 15% accuracy range. It is highly probable that most players will have an average accuracy. However, as we approach 100% accuracy, the probability of a player being assigned a high value decreases exponentially. Additionally, the generator is set up to never generate a 100% accurate player. The rest of these distributions follow a similar logic. This one's almost the exact same type of distribution, except it's on a scale of from 0 to 20. This is set up in a way where it's equally likely to be 100 to have 100 previous games played and 300 previous games played. And it's a Gaussian distribution. So lastly, how do you really, when you match players up into their pairs, how do you eliminate the players? So this flowchart describes what the code does for each player when they're both paired up. First, you take both of the players' parameters and put them into an equation that weights them against each other. Then you generate player A score and then player B score. From these, you create the probability of a player winning by putting player A score over the sum of A plus B, and the same thing for B. And then you take a random choice that takes these probabilities into account and takes a winner. So for instance, if player A has a 60% chance of winning, or has a 60% chance of winning through the score, the random choice has a 60% chance of choosing player A. Then it returns the winner. A quick graph of how this works is if you have a player that hits 1% of the shots, they've played 200 games previously, and they've also played one other first-person shooter. This distribution kind of shows that where this graph shows data where you take a player with these parameters on the left and calculates the probability that they would win against 100 randomly generated players. So it's a histogram of this right here, their probability of winning. And we can see that this kind of distribution makes a lot of sense. For a player that only hits 1% of their shots, they don't really have a great probability of winning against almost every player. But this is kind of what we want, right? They don't have a great probability, but it's not impossible for them to win, which is good when we are trying to test very low skill players and see how many times it takes for them to win one game. So how many simulations it takes for them to win one game. So in summary, this is kind of the flow of how you do this. You would do this many, many times to derive significant statistics from this. And then every time per simulation, of course, you would add one to Fortnite experience to kind of simulate skill growth as you learn something from every game you play. So into the more analysis part of my presentation, how does player statistics change game outcomes? What are we looking for? So first, we're looking at the probability of winning after n simulations. Say you simulate 5,000 times. We want to know the amount of games that you've won out of those 5,000 times, and that will closely approximate the probability of you winning any game, right? So if you're going to go on to simulation 5001, you would have a 2.5% chance of winning that. This simulation helps generate that number, or this way of looking at the simulation generates that number. Then we take the mean minimum simulations it takes to win a game. So we want to find how many simulations it takes for a certain player to win a game, and then we do that multiple times, and then we take the mean of that so we can closely approximate how many games it takes for a person to have a 50% chance at winning a simulation. So setting up the simulation, we set two player parameters, accuracy, and it could be accuracy, it could be FPS game players played, or FPS games played, and previous Fortnite games played, and then we set an array of the third parameter that we want to test. So for each value in the third parameter array, we simulate n rounds and return the fraction of rounds 1 over the total number of simulations. That's question 1 on the previous slide. So our first thing here is that We are testing game experience. So we want to set Fortnite games played to 250 with normal growth at 1 every simulation, and 20 samples of first-person shooter experience from 0 to 25. That's the parameter we're testing, and the accuracy is set to 15%. So we take 1,000 simulations of accuracy per accuracy sample for a total of 20,000 simulations. This can end up to be, you can increase this by a lot, but it really increases the computational time significantly to a point where it becomes unusable because it's taking so long, which I thought was interesting. But looking at this graph, we can see after game experience hits 25, it really increases the total, the percentage of winning by 3.5%. So, which isn't very significant, but it shows that there's a positive relationship here, and game experience does affect your skill level in Fortnite, which makes sense, right? Then we are testing games played, and with 50 samples from 0 to 500 games played, FPS experience is set to 5 and accuracy is set to 15%, with 1,000 simulations per accuracy sample, with a total of 5,000 simulations. So right here we have games played. At 500 games played, the probability of winning is at about 5.5% to 6%. And again, this isn't very significant when you consider this next one. It's greater than game experience, of course. It's just, everything here is significant, but when in comparison to accuracy, it really doesn't. Accuracy really shows that it is the most significant parameter in this equation. So games played is set to 250 with normal growth and 5% or 5 FPS experience and 15 accuracy percentage samples with 5,000 simulations per accuracy sample with a total of 75,000 simulations. We can see at accuracy number, at 90+% accuracy, you have a person wins about 16% of the 5,000 games that they were simulated on. So, which makes sense because somebody who hits 90% of their shots is bound to win a lot. So we want to find the minimum games to get a win. We want to be able to retool the simulation functions in order to quit when the player has won 1 simulation. We repeat this many times to get a distribution of minimum games. However, the player parameters remain static, so we can't really test a lot of these things or test accuracy over time, as it would be difficult. We would do way too many simulations for my computer to handle. So regarding normal player parameters, I would say that this guy has 30% accuracy, 100 previous games played, and 5 game experience. And then we do 100 iterations of sim to win. This is a histogram of the sim to win simulations. This guy right here had one time where it took him 100 games to get 1 win. So we did use this type of logic and did this 100 different times and found that the mean was about 62.58%, or 58 games. So we can say that it would take about 62.58 simulations to have for a player with these parameters to have a 50% chance at winning a game. And you compare that to skill player parameters. This guy, it's very different. This guy only has to play 1 game to win, or do 1 simulation to win. So he's done this 30+ times. So a player with these parameters is obviously very successful and has a high probability of winning and doesn't have to play many games to win at least once. So we can say with these parameters, it will only take 1 to 3 games to win once, which makes sense considering that accuracy is very predictive of the player's probability of winning. Finally, how does our skill change player outcomes? How does skill change over time? I can talk. So measuring skill gain over simulations. We know that every simulation that the player plays +1 is added to the player's total games played. So this kind of models our basic growth in skill. In order to measure this, we want we want to keep track of when the player was eliminated every simulation. And then players should, on average, have slightly higher placements every game. So that would be expected, as if you're growing, as your skill is slowly growing over time, you should have slightly higher and higher placements. You should be eliminated like you should be the 81st person to be eliminated instead of like the 3rd person to be eliminated, and that should happen more often. So to set up the simulation, we're going to take a pretty average Fortnite player with a low experience and take 300 simulations with a bar graph of placements each simulation. Trend should look like this, but it really doesn't. It's a messy graph. Doesn't seem that there's any real correlation here. Can't really group bins without misrepresenting data. You see here simulation number really low early in the simulation process. This guy placed like 92nd or 98th here, but I mean, even at the end of the simulation, he's still having a lot of these high placements. So we really can't say that skill growth affects it that much. If we wanted to fit a regression model, check the correlation, it kind of proves that. Just no correlation coefficient, and even if there was, the R-square would be so high that it wouldn't matter. So this agrees with the previous findings of relative importance of games played on winning percentages. So accuracy is a lot more predictive of that. So if accuracy was changing by a large amount every game, then this might look a little bit different. But this is very noisy data. This could be normalized through different statistical methods like z-scores, but that's beyond the scope of our class. Finally, our conclusions. Is simulating Fortnite games possible? Yes, it is, with probabilities. What are its limitations? Unfortunately, a lot. You have to cut out a lot in order to have an efficient simulation. However, our simulation is somewhat representative of real life, I would say. I don't really have much data to compare it to, but it makes sense. So our second research question, how do player statistics change game outcomes? We can see that player accuracy has a large effect on player probability of winning. And through simulating a lot of times, we are able to see that we can generate the mean minimum amount of games played for each player for a given player parameter, which is interesting. And then when we look at skill growth over time, we can see that the way that this simulation handles skill growth, it really doesn't affect the player outcomes that much. The probability is still pretty the same, and the variance just overtakes any significant player growth. So this is my conclusion. It's a very, very long one. I apologize for that. If you want to learn more, I don't know if you'll be able to see my Jupyter notebook, but I guess you can try. Again, I apologize for this being so long, but I went really hard on this, and I can't really shorten this up a lot. And if I talk too much or too fast, I'm not going to cover enough, or I'm going to skip over a lot, and it's going to be hard to listen to me. So thank you for watching if you're here, and I look forward to your questions. Thank you.